Declarative UI frameworks rely on a specific automation. The developer describes the interface state, and the system manages the rendering loop. Within this model, views are transient descriptions of the interface. They are stack allocated and disposable, designed to be created, evaluated, and destroyed by the framework up to 120 times a second. But the underlying application data behaves differently. Maintaining state requires persistent, heap-allocated memory structures that stay anchored even as the visual interface above them is constantly recycled. This creates a direct engineering tension. The system must coordinate these disposable UI constructs with persistent state models without introducing latency into the rendering cycle. On modern hardware, this cycle is governed by a strict constraint. To maintain fluid animations, the primary UI thread, the main actor, must complete its work within an 8-millisecond window to reach a 120 Hz refresh rate. If a synchronous file operation or a heavy memory reallocation executes on this specific thread, the 8-millisecond window collapses. When the main actor is forced to wait for I/O or redundant allocations, the interface freezes. While the background processor cores remain idle, the user-facing thread stalls, causing visible stuttering. Modern frameworks mitigate this by moving state management rules to compile time macros and shifting heavy I/O operations into asynchronous background thread pools. Solving this performance bottleneck requires an architecture that respects hardware boundaries. We have to look at how the compiler handles local memory first, before addressing how data meets the disk. The first optimization addresses memory management at the view level, specifically how complex models are initialized within the interface hierarchy. In this code sample, a view model is declared and instantiated directly inline. This is a common pattern for managing local state. Historically, system property wrappers used a deferred initialization technique. This executed the setup code only when the view physically loaded into the active hierarchy. This protection was lost during the initial transition to modern observability protocols. Without that built-in deferral, early implementations of these modern state wrappers evaluated their initializers immediately and synchronously as part of the view's construction. This introduces an O(n) allocation problem. Every time a parent view reevaluates, it recreates its child structs. Because the initializer is synchronous, the system reruns the view model's setup code every time the parent updates. If that initializer performs expensive work, like reading a preference file or establishing a database connection, the repeated execution creates a significant CPU choke point. This means that migrating to highly efficient observation protocols actually decreased performance in enterprise applications by introducing redundant, heavy work on every frame. To resolve this without manual boilerplate, the toolchain shifted the state binding logic from the runtime to the compiler. The state wrapper is now a macro. At compile time, the code expands into an abstract syntax tree that restructures memory allocation. The compiler synthesizes hidden backing storage tied directly to the view's persistent identity in the render tree. This converts the assignment into a computed accessor. The initializer executes exactly once when the storage is created, regardless of how many times the parent reevaluates the child. Moving to the macro level removes the O(n) initialization cost. Setup code is completely deferred until the view is ready to render. However, this compile time logic enforces strict initialization rules that didn't exist in the older runtime-based systems. If you assign a value at declaration and again in a custom initializer, the compiler will throw a premature use of self error. Because the macro already synthesized the memory layout, strict initialization rules prevent you from accessing the property before the view struct is ready. The fix is straightforward. Consolidate state definition and initial setup in one place. Initialize inline or within the constructor, never both. This macro-driven approach provides the predictability required for large-scale applications to manage complex models without triggering redundant processing spikes. While local memory management adjusts interface fluidness, large-scale disk operations require an entirely different architectural strategy. Professional tools manage gigabytes of assets. Serializing that much data to a physical disk is a highly resource-intensive process that takes hundreds of milliseconds. Legacy document architectures combine state retention and file serialization into single monolithic objects. This tightly coupled the application data to the physical file system. Because these operations often occurred synchronously on the main actor, An autosave operation would routinely block the UI thread, causing the application to hang during heavy I/O. This is why the older document protocols have been replaced. The system now uses a decoupled tripart architecture, consisting of separate reader, writer, and document state protocols. This structure forces file operations into background worker threads. Using explicit concurrency annotations prevent I/O tasks from ever inheriting main thread isolation. By separating the editing model from the physical writing process, the application shields the user's interactions from the inherent latency of the file system. To move data across these thread boundaries safely, the framework uses a three-step transactional pipeline. First, on the main actor, the system calls a snapshot method, creating an immutable copy of the state. Because this copy is brief, the UI thread is immediately released. The user can continue working while file writing begins in the background. The system then hands this immutable snapshot to an asynchronous background writer, which handles the heavy encoding and disk access independently. But even when running securely in the background, rewriting an entire multi-gigabyte file package for every minor change is deeply inefficient. To optimize this, the writer receives both the current snapshot and the previously successfully saved snapshot. This allows for delta-based saving. By comparing the two snapshots, the writer can identify exactly which assets inside a file package have changed. The writer then updates only the specific resource files that mutated, rather than rewriting the entire package structure to disk. Any long-running operations during this process update a unified progress object, allowing the UI to reflect the saving status without requiring manual thread hopping code. These transactional handoffs allow the system to maintain interface responsiveness, even when processing the complex serialization required for massive creative assets. Modern state and document systems are designed to bridge the gap between high-frequency UI updates and high-latency disk operations. The goal is an architecture where local memory management is governed by compile time guarantees, and disk access is restricted to asynchronous concurrent boundaries. As shown here, when these two systems work together, the main actor stays free to handle user input, while background threads manage data persistence. These mechanisms, lazy evaluation, safe transactional handoffs, and actor isolation, ensure that the application's performance remains stable as the data complexity scales. By looking past the high-level syntax to understand these runtime boundaries, you can build software that operates in alignment with the underlying hardware constraints.